Today, we are diving into one of the most powerful tools in statistics, the binomial probability distribution. Now, it's specifically designed for situations where there are only two possible outcomes. And yeah, that might sound almost too simple, but you're about to see just how many complex, real-world problems it can actually solve.
I mean, just think about it for a second. How many things in our daily lives, when you really boil them down, come down to a simple yes or no, a win or a loss? You either get the job or you don't. A light switch is either on or it's off. Success or failure.
And this isn't just some philosophical thought experiment, you know? This binary choice is the absolute foundation for massive decisions. Think about it. A new drug either works for a patient or it doesn't. A microchip rolling off an assembly line is either perfect or it's defective. Understanding the odds in these situations is, well, it's absolutely critical. So here's our game plan for today. First, we're going to figure out what kind of job requires this tool. In other words, what exactly is a binomial experiment? Then we'll pop the hood and take apart the formula itself. After that, we'll look at the blueprint, the quick ways to find averages and see how the data spreads out. And finally, we'll get to the masterclass where we see this tool in action.
Okay, first things first. We have to know when we can actually use this thing. You can't just throw the binomial distribution at any old problem. It has to fit 4 very specific conditions. Seriously, get these 4 rules down and you are already halfway to mastering this.
So here they are, the 4 non-negotiables. 1, you need a fixed number of trials. Think flipping a coin exactly 10 times, not just whenever you feel like it. 2, each of those trials has to be independent. My first coin flip has no impact on my second one. 3, you can only have 2 outcomes, heads or tails, success or failure. And finally, number 4, the probability of success has to stay the same every single time. For a fair coin, that's always going to be 50-50 on the first flip, the 5th flip, and the last flip.
And let's clear up a really common point of confusion right now. In statistics, the word success doesn't always mean something good happened. Not at all. It's just a label we give to the specific outcome we're counting. So if you're a quality control manager, your success for the day might actually be finding a defective part. It's all about what you're measuring.
All right, so we know the job. We know what kind of problem we're looking for. Now, let's look at the tool itself. This is the formula that does all the heavy lifting. And I know, it might look a little intimidating at first, but trust me, we're going to break it down into a couple of simple, logical pieces.
And there it is, in all its glory. This beautiful little equation tells us the exact probability of getting a specific number of successes, x, in a certain number of trials, n. But what does all that alphabet soup and all those symbols actually mean?
You can really think of the formula as having 2 main jobs. The first part, that NCX thing, is what we call the counter. All it does is count how many different ways you can get the outcome you want. Let's say getting 2 heads in 3 coin flips, well, that can happen 3 different ways. The second part of the formula calculates the actual probability of any single one of those ways happening. You just multiply the 2 parts together, the number of ways times the probability of one way, and boom, you've got your answer.
Now, calculating the probability for every single possible outcome can be a little tedious. A lot of the time, you just need the big picture, right? Like, what's the average result going to be, and how spread out is the data? Luckily for us, there are 2 super simple shortcuts for that. And seriously, the best part is that these formulas are surprisingly easy. The mean, which is just the expected number of successes you'd get, is literally just n times p. That's it. The standard deviation, which tells you how much the results typically vary, also has a really straightforward formula. These are fantastic for getting a quick snapshot of what to expect from your experiment. But it's not just about the numbers. We can actually visualize these probabilities, and when you plot them on a graph, they create a very distinct shape. The one thing that decides what that shape looks like is p, the probability of success. This gives us a fantastic visual shortcut. See, when the probability of success is low, when p is less than 0.5, most of your results are going to have very few successes. So the data piles up on the left side, creating a long tail to the right. We call that skewed right. And if success is very likely, the opposite happens. The data piles up on the right, and we get a left skew. But when p is right around 0.5, like a coin flip, you get that perfect symmetric bell-shaped curve that everyone knows. Okay, so we've got the big picture.
let's quickly cover a few common traps to avoid when you're doing the calculations. First, pay attention to the wording. At least 3 is not the same as more than 3. Also, don't forget the complement rule. Sometimes it's way easier to calculate the probability of something not happening and just subtract that from 1. And always, always double-check that your trials are actually independent.
All right, we have covered the theory. For this last part, let's see why any of this really matters. I promise you, this is not just some abstract exercise for a textbook. This tool is used every single day to make incredibly important decisions.
The applications are honestly everywhere. In a factory, it determines if an entire batch of products passes inspection based on a tiny sample. In medicine, it's absolutely essential for figuring out if a new drug is actually effective. You'll even see it in marketing, in finance, and in political polling to predict outcomes.
And this is the kind of question that brings it all home. This isn't abstract anymore, is it? This is a real, tangible question a pharmaceutical company needs a solid answer to. And with the binomial distribution, you now have the exact tool to figure it out. You can calculate that precise probability and give them a concrete, data-driven answer. So there you have it. You have the complete toolkit now. You know the 4 conditions to identify the right problem, you have the formula to calculate the exact probabilities, and you've got the shortcuts to see the big picture. The only question left is, what problem are you going to solve?